All right, in this video, we're going to talk about our third kind of conical section, which is the hyperbola. The hyperbola, if I have my three-dimensional three-dimensional cone, where it kind of looks like the hourglass, so I got an inverted cone on both sides, and the intersection between that cone and a plane forms the hyperbola in terms of their intersections. Now, an application for the hyperbola can be related to the sonic boom for airplanes. So when airplanes break the sound barrier, you get that loud boom. Well, the interesting thing is that this cone of the sonic boom, and for where it can be heard, and where that cone intersects the ground forms a hyperbola, and we only see one side because the boom isn't necessarily here in front. We're looking at the one behind it. Every single point that lies on this curve or inside of that curve will hear the sonic boom. Everything that is outside of that hyperbola will not hear the boom when the plane breaks the sound barrier, which is pretty interesting. I guess if you were technically standing very close, you could have two people standing next to each other. One could hear the boom and one could not hear the boom based on where they were located for that hyperbola. So a hyperbola is going to be the set of all points whose distances from the two fixed points called the foci will have a constant difference. Now, I can see that in terms of our equation because we'll have subtraction between the squared terms. So I've had x squared term minus a y squared term, regardless of the orientation, y squared minus an x squared term. The hyperbola has two axes of symmetry. It has a transverse axis, which has endpoints of the vertices, and it has a conjugate axis, which actually does not lie on the curve. The interesting thing about the transverse axis is the transverse axis is not actually always longer than the conjugate axis. One could be greater than the other. And we're going to let our constant A represent the distance from the center of the hyperbola to a vertex, and our constant B is going to represent the distance from the center to the conjugate axis, one of the conjugate axis endpoints. Now, C is still going to be the distance from the center to the foci, or either focus, whichever the orientation is. Now, we have a Pythagorean relation for our hyperbola, where the greatest distance is going to be the distance from the center to a focus. So it's going to be c squared equals a squared plus b squared. So let's look at a graph here, and we'll do the one where it's oriented left and right. So the hyperbola itself is in black. Now, it's a very busy picture because it has everything that's on it. We have our center here at the middle. Distance from the center to the vertex is going to be a. That's half of our transverse axis. Our conjugate axis, which in this case goes up and down, the distance from the center to the conjugate axis endpoint is going to be b. Notice how the hyperbola, which I have on facing opposite directions, never touches the conjugate axis. I have the transverse axis and conjugate axis form a right triangle. The distance from a center to a focus C is going to be the same as the distance from the vertex to a conjugate axis endpoint. And what we have here is we have a right triangle. We have a right triangle where the distance from the center to the vertex A is one leg, B is another leg, C is the hypotenuse. And so we get our Pythagorean relation as being c squared equals a squared plus b squared. Another thing to notice is, notice how the focus is the biggest distance. It actually is less distance to go to the vertex than it is to the focus. So C is the bigger of the three constants. Also notice how we have asymptote lines that bound the ends of the hyperbola. Now when it comes to writing the equation of the asymptotes, it depends on the orientation. Now we start with the center, H and K. All right, so H and K are inside of our equation no matter what for our equation of our line, but the slope is the part we got to be careful with. So what I do is I start with my center, and now if I draw a central rectangle, which is based on lines that are parallel to the conjugate axis and the transverse axis, the asymptote will have a slope of the diagonals, both of the diagonals. So if I start at the center, and if my hyperbola opens to the right or left, you figure out how do you get to the top right corner. I go up B, right A. So my slope will be positive B over positive A. But if I wanted the other asymptote, I go up B, left A, which would be negative. If I was oriented the other direction, where it was opened up or downward, the asymptote, I still would start at the center, figure out how to get to the top right corner. If it's oriented up and downward, I would go up A, right B, so that would be the slope there. Eccentricity, which is the ratio of the distance from the center to the focus compared to the distance from the center to the vertex, C over A, is still the same as it was for the ellipse. The difference is, since the distance from the center to the focus is greater than the distance from the center to the vertex, the eccentricity of a hyperbola is always bigger than 1. All right, so now we're going to graph and identify some of these key features of hyperbolas, and we got two examples. So one where we're oriented vertically and one where we're oriented horizontally. So I'm given this equation here. Now the big question is well, how do I know it's a hyperbola? I know it's a hyperbola because both y and x's are squared, and we are subtracting because of the way we define the hyperbola as the set of all points that have a constant difference between the two foci. So we'll begin by finding the center. So my center should be h comma k. So I'd have an x value of 1, y value of -1 for my center. So my center would be at 1, -1. The orientation here. The best way to tell you how to determine the orientation is based on what is the non-negative term, what's in front of the subtraction. Since y is in front of the subtraction, this orientation is going to be vertical. It's going to open up and down. Now that I know that it's vertical, now I can now identify what A and B are. I do not identify A and B based on size. I identify A and B based on A is the denominator of the non-negative term and B is the denominator of the negative term. And so A in our case is going to be 4, B in this case is going to be 3, and we do the Pythagorean relation, so C squared is going to equal A squared plus B squared, and so C is going to wind up being 5. And so we get 16 plus 9, not 9 squared, is going to make 5. So our vertices here, if we're oriented vertical, a vertex is going to lie above and below the center. So I would add and subtract A to my center to get my vertices. So they're going to have the same x value. I'm going to take away 4, so I got 1, -5 for one vertex, add 4, so we have 1 comma positive 3 for a second vertex. The conjugate axis endpoint is going to be in the other direction, so instead of up and down, it's going to be right and left of our center. And so we'd have a conjugate axis endpoint at -2, -1, and we have a conjugate axis endpoint at 4, -1. And then our foci are going to be in the same direction as our vertices are, so it would lie above and below our center, just like our vertices were. So we'd have 1 comma -1 minus 5 -6, and then 1 comma -1 plus 5 be positive 4. And I skipped the asymptotes for last, and we have our eccentricity, which would be C over A, so 5 over 4. Notice our eccentricity is bigger than 1. It's supposed to be. All right, so now we're ready to graph. So we have a center at 1, -1. I'm going to indicate that with an X. All right, our vertices are at 1, -5. So I'll put a V. And at 1, positive 3. All right, we have foci. It's one of them is at 1, 4. And then we have another one that's at 1, -6. Okay, and then we have conjugate axis endpoints at -2, -1. So I'm just going to say CA, and then at 4, -1. And then we want to sketch. So in order to sketch, what we're going to do is we're going to make a central rectangle, kind of like what we did for the ellipse. So parallel to our transverse and conjugate axes. But the endpoints are our vertices and the conjugate axis endpoints, not the foci. So we have our rectangle. To graph our hyperbola, we need to first make our asymptote lines, where our asymptote lines are going to be diagonal. So we start at our center, and then we would work our way to the top right corner and the bottom left corner of the rectangle. Now, as soon as I do that, I need to go write that equation. Well, our asymptote here would be y equals, you'd take the y value of the center, so -1, and then plus, we would have our slope, which we'll get to in a second, times x minus the x value of the center. Now, the slope here of this line, I would start at my center, I would go up and right. So now looking at the orientation here, we'd go up A, right B. And so we'd have positive 4 over 3 for our slope. Now, my other line for my diagonal, I would just go with my center and I would go up and left. And so it would wind up being up A, left B. So I could just say we would have -1 plus or minus 4/3 times x minus 1. Now, to graph our ellipse, or excuse me, to graph our hyperbola, we would start at our vertex, and then we would work our way towards those asymptotes that would contain our hyperbola. All right, here look at this next one. So we have a x squared term and a y squared term that are subtracting. So we have another hyperbola that we want to graph and find all key features of. We'll start by finding the center. So it should be x minus h and y minus k, where h and k are our center. So here we'd have a center at 3, -2. The orientation here for this is you go find what term is positive. So since x is in front, the orientation here is going to be horizontal. So now we're going to go figure out our vertices and conjugate axis endpoints. Well, in order to do that, I got to figure out my constants a, b, and c. Now, a is going to be the square root of the denominator that is the non-negative term. So a is going to be, in this case, the square root of 36, which would be 6. B is going to be the square root of the term that's behind the minus, would be the square root of 64, which is 8. And then we would go solve for c. Now, the Pythagorean relation, c squared is equal to a squared plus b squared. And then we would solve for c. And we wind up getting a c value here of 10. So we have all of our constants. Now, since it's going to be horizontal, the orientation, that means our vertices are going to be left and right of the center. So one vertex, I would do 3 minus a, so it would be -3, comma, -2. The other vertex would be at 9, -2. So plus or minus a to get my vertices. Conjugate axis endpoints, plus or minus b in the other direction, so it'd be 3, comma, now b is 8, so -2 minus 8, so I have one endpoint at -10, and then I have another endpoint for my conjugate axis at -2 plus 8, which would be +6. Our foci are in the same direction as the vertices are, so in this case we're add and subtract 10, one focus would be at -7, -2, and we're adding and subtracting c to our center, and the other focus will be to the right, so 3 plus 10, which is 13, will be my x value, y value of -2. We'll do our eccentricity next and save our asymptotes for the end after we graph it. And so eccentricity c over a, 10 over 6, which makes 5 over 3. Notice how that's bigger than 1, and that's the way it is every time for a hyperbola. All right, so we'll start by graphing our center. We have a center at 3, -2. I'll put a little x right there. We have a vertex at -3, -2. So put a dot there with a little v, and we have another one at 9, -2. We have foci at -7, -2, and 13, -2. Notice how all those are on the same line there, the focal axis. We have conjugate axis endpoints here at 3, -10, so I'll say CA, and at 3, 6. Now what we'll do is we'll make our central rectangle. So rectangle passes through the vertices and the conjugate axis endpoints, not through the foci. They're parallel to the conjugate axis and the transverse axis. Remember, the transverse axis connects the vertices together. Now, before we start graphing our actual ellipse, we want to make our diagonals, which represents the asymptotes. So I have one asymptote that's a diagonal. Here, start at the center. So if I'm going to go write the equation, it'd be y is equal to the y value of the center. Then I have my slope, and then, which we'll get to in a second, times x minus the x value of the center. Well, the slope here, if we start at our center, we got to go up and right to get to that top corner. We would go up b, right a. So it'd be up b over a. Well, b we got to be 8. A we got to be 6. So 8 over 6, 4 over 3. So we have plus 4 over 3 times x minus 3. That's one of our asymptotes. Now the other asymptote, the other diagonal, we'd start at our center and work our way up to the top left corner, which would be the same ratio up b over a, but in this case it'd be negative, so I could just say our asymptotes would be negative 2 plus or minus 4 over 3 times x minus 3. Now that we have our asymptotes, we can draw our curve, which we'd start with our vertex, and then we would make our hyperbola go towards the asymptotes, because that's what's going to bound the ends of our hyperbola.